Okay, so let me remind you what we were doing. We were saying the following. We were saying that Hopf algebras can constitute a useful tool to compute Mobius functions of posets. The way this works is that we said that if you're in the incidence Hopf algebra of posets, so maybe you look at the all possible posets modulo isomorphism, if you can find the antipode so here S is the antipode for a poset or for a family of posets, then you can find the Mobius function via the composition of the zeta function with the antipode. Okay. So this is again the antipode. And to remind you about this function zeta, this is the pretty trivial function that sends everybody to 1. Zeta of any poset is equal to 1. Okay. I'm sorry? That's right. So here, I guess I should be saying interval the whole time. So,
no, I mean the zeta function.
but here also, right? Because the elements of the incidence Hopf algebra of posets are intervals. They have to have a bottom and a top. And so, if I want to be more precise, I should really be saying interval here. Okay. But this is the point. The point is basically that if you have a formula for the antipode, then you get a formula for the Mobius function. Okay? I'm very excited about this because I love Mobius functions. You're probably not so excited because maybe you don't know what this Mobius function is good for. Okay? And so, I mean, you know a little bit about it. You proved a couple of things about it. But so what I was going to do today is just give you kind of a crash course on Mobius functions and how they're useful in combinatorics. So that's my plan for today. Mobius functions of posets. Okay. So let me remind you how this went. In the incidence algebra, of all posets of intervals, let me say posets with a 0 and a 1, because when you say interval, it sounds like you're a part of something bigger, and all I mean is posets with a bottom and a top element. Yeah? So the question is, what if I don't know what the antipode is? What if I cannot find a good formula? The antipode always exists in a Hopf algebra. The question is whether you can find a nice formula for it or not. And that means that the Mobius function also exists, but maybe you can find a nice formula, maybe not. We will see that sometimes the Mobius function has a nice formula, And it's not so easy to see it with the antipode. So sometimes it's great. Sometimes it's great because the antipode is nice and you can use it to find the Mobius function. But sometimes the antipode doesn't do such a good job when you try to apply this. And you'll see what I mean by that. Yeah?
Can you ever go backwards?
So the question now is if I know mu, can I find S? And the answer is that in principle, no, because this formula cannot be reversed. You can't invert sigma inverse, zeta inverse. If you think about it, you'll see that you can't say S is sigma zeta inverse mu. The domains and ranges don't match. So no, you cannot find S from mu given this formula, but it's more like if you have a good formula for mu, that might give you an indication of what S might look like. So mu gives you partial information about S. Okay, so we had the following functions. So we had the function 1, which is 1 if x is equal to y and 0 if x is less than y. Okay, and we saw that this was the identity under convolution. Okay, we also had the functions zeta, which was defined to be 1 for all intervals. And then we defined mu to be the inverse of zeta under convolution. Now I should remind you, convolution does not give you a group, so it's not automatic that you have an inverse. But we proved that you have an inverse. You did this in your homework, and you showed that this definition makes sense. Zeta has a unique inverse, and we call it mu. Okay, but I want to think about. I mean, this is the definition, but this is a definition that I think is kind of hard to get excited about. It's just okay, some inverse of something that. I mean, for example, it's not clear given that definition how you're supposed to even compute an example. Okay? So let's think a little bit more about what this means. This means that mu convoluted with zeta gives you 1. Right? So let's apply this to some interval from x to y. Okay? And so what does that mean? Well, if we apply this convolution for the interval from x to y, then we're going to be summing over all the numbers, all the elements zeta inside the interval of mu of x z times zeta of zy, and we're going to get this equal to 1 of xy. This is the convolution product. And what is 1 of xy? It's this. Right? So this is equal to 1 if x is equal to y, and 0 otherwise. Okay? Now, the only reason that I use blue for this is that blue doesn't show up too well in the camera. So if you're watching this on video, you can't see this, and that's great, because it's 1. Right? Just 1, and so this equation is also true, even if you can't see the blue. This is just 1 for every value of zeta and y, right? And so this is actually a defining property of the Mobius function. Okay, let's think about it a little bit more. So if x is equal to y, what does this say? It says mu of xx is equal to 1, right? That's what this says when x is equal to y. Because if x is equal to y, then the only summand here is, if you have to be between x and x, you have to be x. And so you get mu of xx is 1. Now what if x is not equal to y? Then you're summing over all the different z's between x and y, right? And in particular, one of the summands is z equals y. Okay? And so this is one of the summands, and that summand has to be the negative of the other ones so that everything adds up to 0. And so I can write this as follows. Okay? So this summation is the exact same summation, except that I dropped the term z equals y, which is precisely this one. So when I send this over, I get that this plus this is 0. Okay? The reason this is useful is that, I mean, actually, this is the way that the Mobius function is more often defined. I claim that this defines it completely recursively. Okay? Because it says, okay, if you need to find the Mobius number between x and y, then you do the following. You say if x and y are equal to each other, it's 1. And if x and y are not equal to each other, then this gives you a recursive formula for this in terms of smaller values of z. Okay? So this is a recursive formula for the Mobius function, and this is the way you'll see it defined in books very often. Okay? So this is, you can think of this as, and by the way, this equation is exactly the same as this equation. Right? It's just not using the language of incidence algebras, and so this you can think of as the definition of the Mobius function. Okay? Now, let me say that usually the P is a fixed poset, and the way that we usually like to think of this is P is a fixed poset, and then mu we think of as a function from the intervals of P to, really it ends up, I mean, in principle it's to K. So here, these are just all the intervals in P. Okay, so here's P. Then for every interval between x and y, you assign a Mobius number. Okay, and so let's think about what this recursion says now. It says that if the interval is trivial, then the Mobius number is 1. And if it's not trivial, then what you do is that you look at all the elements in this interval, okay? And you assume that you already computed mu of this, mu of this, mu of this, all of those mu's. You add all of those, and then you switch the sign, and that's how you get mu of xy. That's what I mean by recursive. So given that I computed mu of x, comma, z for every z which is lower than y, I know how to compute mu of xy. Question? Okay. Okay. And so this is the Mobius function. This is how it's defined recursively. But I should say that often we are only interested in mu of the bottom, comma. I mean, you're supposed to do, the Mobius function is defined for any x and y with x less than y. But in many circumstances, you only care about the Mobius number between the bottom and x for all x. Okay? So we can also define mu of x to be mu of the bottom element, comma, x. Okay, this is a definition. So when mu is only given one argument, then it is assumed that the first argument is 0 and the second argument is the one that you have written. Okay? And the other thing that we define is that I mean, this is not the best notation, but this is what people do. So also sometimes you see mu of p, mu of the poset. So what should that be? Well, it's just the Mobius function at 0, 1. Okay? So mu of this is equal to mu of 1, which is also equal to mu of 0, 1. Okay? Sometimes this is called the Mobius number of the poset, and so it has a name also. Okay? And while I'm making definitions, let me make a last definition. That if P is ranked, okay, so if your poset has floors, then we define the characteristic polynomial of P is the following thing. So it's again, the notation is a little bit unfortunate because for us chi has been a character, but usually people write the characteristic polynomial chi. So I think it won't be ambiguous because this looks like this. Okay. And so you know, it has the name of the poset underneath it and the name of the variable here. So maybe now it doesn't look so much like a character. What is this? What you do is that you sum over all your elements of the poset mu of the element and q to the basically the rank, except that we do it backwards. And so it's the rank but counting from the top. Okay, so rank of p minus rank of x. So rank counting from the top. Okay. So far this is just a bunch of definitions, and I'm hoping to get you excited about them over the course of the rest of the class. Yeah? Okay, so let's compute some examples just to see what this looks like. So here's a poset that I like. This is the Boolean Postit B3. Okay? And let's compute the Mobius function. And now, in principle, to compute the Mobius function, I need to compute it for every pair of elements. But let me just compute this one. Okay? I'm going to compute mu of the elements, and I'm going to write them in blue. So what did we say? We say first you start for the trivial interval 0, 0. Okay? And mu of the trivial interval is 1. Okay? And then you start working your way up the posets, and you say, okay, for this element, mu of 0, this element is minus the mu's below it. Okay? So the only element below it is 1, so you get a minus 1 here. The only element below this one is this one, so you get a minus 1. The only element below this one is this one, you get a minus 1. Then we go here, and we say, okay, who's below this element? This minus 1, and this 1. They add up to minus 1. I switch the sign, so I get 1. Okay. Basically, what I'm doing is making sure that below every element, the things add up to 0. Right? 1 minus 1 minus 1 and 1. So below this element, I have this one, this one, this one, and this one, so I should also put a 1. And below this element, I have this one, and this one, so I should also put a 1. Okay. Finally, here I look at all the things below it. So you see I have 3 1s, 3 minus 1s, and a 1, and I need everything to add up to 0. So I need to put a minus 1. Okay. So maybe you have a conjecture about the Mobius function of Bn. Yeah. I mean, we don't have so much evidence, but at least for B3, 1 minus 1, 1 minus 1. It might be. Okay. What is the characteristic polynomial? I said you basically add up the mu's according to rank. Okay? And so we're just going to do this rank by rank. So here the numbers add up to -1. Here the numbers add up to 3. Here they add up to -3. And here they add up to 1. Okay? And we do the rank, but from here to here. Okay? So this guy gives me a q cubed because I start 0, 1, 2, 3. Okay? So I get q cubed. Then this guy contributes q squared. These guys contribute q. And this guy contributes just 1. Okay? So in the end, what do I get? Q cubed minus 3q squared plus 3q minus 1. So you know what that is, right? There's a better name for this. This is called q minus 1 cubed. And so maybe you have a conjecture for what the characteristic polynomial of Bn might be. But is it clear how I'm computing these numbers in this polynomial? Yeah?
So can you tell me again, not from the bottom level or the one right above it, but where you have all the ones?
Here?
Positive ones. Can you show me again how you got the one?
Sure. So let's look at how I got this one. I look at what elements are below it. But by below it, I mean less than in the poset. I don't mean lower in the picture. I mean less than in the poset. So that's this one, and this one. And those numbers need to add up to 0. So if I have 1 minus 1 minus 1, then I need a 1.
And same goes with that middle one, because it's your -1.
Right. Yeah. Maybe it's more interesting to compute a less symmetric example, and then you'll see that the numbers get to be a little bit stranger. But in this very highly symmetric example, you should expect that things look very similar. At least because of the symmetry of Bn, you should expect that at each point in a given height, the number should be 1 just by the symmetry of the poset. Okay. Question?
So in the rank poset, everything of rank 1 is going to be -1.
That's right. So it always starts 1, then minus 1s, and then it gets crazy maybe. Here it didn't get too crazy, but it can. Okay.
So it doesn't always give you information about the width of the poset, does it?
Yeah, I mean, it gives you limited information about the poset, but I mean, does it tell you what the width is? Well, I mean, it doesn't, but these are kind of tricky combinatorics questions that are great to ask, but maybe we won't get into them too much right now. Okay? But it's a great question. Given the characteristic polynomial, what do you know about the poset? You know some things, and you don't know others. And we'll see some things that you know. Okay? Let me try to. Let's actually prove some theorems now. Okay? So. So let's do the example where the poset is the Boolean Postit Bn. Okay, so remember that these are just the subsets of a set of n elements. Boolean Postit. Because this is kind of what Boolean logic is based on, where the join is union and the meet is intersection. So I think the name comes from Boolean logic, which is the logic of union and intersection. And it's after, I think George is his name, George Boole, who was a pioneer in this stuff. Okay, so one thing I should tell you is that if I gave you enough time and I asked you to prove this pattern, then you could do it. And it's not trivial. It's not impossibly hard. It's a fun exercise in combinatorics. Okay? You can prove that these numbers alternate, and you can prove that the characteristic polynomial really is q minus 1 to the n. I want to show you that we've already done the work to make this a trivial fact, because we know how to do it from the Hopf algebra point of view. You just have to remember something, and okay, so let's just do it. So let's say that you want to compute mu of s comma t. Okay. So one thing that you should notice is the following. If you imagine that I draw here the whole Boolean poset of n elements, okay? And now I want to compute the two-variable Mobius function. So I need to, starting here and ending here, compute this, okay? Now, do you remember what intervals in the Boolean poset look like? They're Boolean, and remember that the reason we knew that is that we knew that this was a hereditary family. And we saw that this thing is exactly isomorphic to the Boolean poset of subsets of somebody. Subsets of whom? Well, the point is that here you're looking at sets that contain S and are contained in T. They all contain S, so if you just throw S out, you get the subsets of T minus S. And so this is isomorphic to the Boolean poset of the set T minus S. Okay? And so basically the Mobius function of S comma T is just going to be the Mobius number of the poset, the Boolean poset of size k, where k is equal to T minus S. The point is that intervals of Boolean posets are Boolean posets, and so to find the Mobius function, I just need to figure out what the Mobius number of bk is. And that's what I'm going to do. So to do that, and I want to apply this formula, I need to know what S of bk is. So do you remember what S of bk was? We already computed this. I had to look it up. I couldn't remember, but we proved. Let me remind you in what context we proved this. We had the incidence algebra of all posets, and we said, okay, now let's look at hereditary families of posets. And the simplest one we could think of was Boolean algebras, and we saw that the incidence Hopf algebra of Boolean posets was something that we call the binomial Hopf algebra. Okay, and you can look it up in your notes. You'll see that I'm not lying to you. And the binomial Hopf algebra had a very simple formula for the antipode. We computed it there, and we found that S of bk was minus 1 to the k bk. So a really simple antipode. Okay? Given that we know this, we immediately know what mu is. Because what is mu? Mu of bk. Well, mu is a composition of zeta and S. Okay, now S of bk is minus 1 to the k bk. And how much is zeta of bk? Well, zeta of anybody is 1. And so this is just minus 1 to the k. Okay. So there it is. No thinking, it just comes out. Okay. And so, I mean, I think some people prefer this proof, and some people will prefer like a clever proof of saying, okay, you know what, let me move combinatorial numbers around. And I happen to like both, but you know, if you try to do it by hand, you're going to have to be a little bit clever and do something more. Here, it just comes out of everything that we've done for free. By the way, if you know that the Mobius numbers really are like this, which we just proved, 1 minus 1, 1 minus 1, then why is it that what we get here is exactly k minus 1 to the n? Well, the reason is that these are all the subsets of a set of size n. And so we have n choose 0 of size 0, n choose 1 of size 1, n choose 2 of size 2, etc. And so all we have here is q to the n minus n choose 1 q to the n minus 1 plus n choose 2 q to the n minus 2, etc., which is exactly the binomial theorem. And so that's it. So we know this, and therefore we know that the characteristic polynomial of bk is just q minus 1 to the k. For free, no thinking necessary. Okay. Let's prove another property of this that is very nice and useful. Yep. That's a good question. So if I give you a poset that has this characteristic polynomial, can you prove that it's the Boolean poset? Or it's related to it somehow? In general, it is not true. In general, this statement is not true. You can have different posets that have the same characteristic polynomial. The Boolean poset is so special that it might be true that if your characteristic polynomial is q minus 1 to the n, then you have to be Boolean. And I'm not sure, and I think that's a nice exercise to think about. I kind of have the feeling that's going to be true, that if the characteristic polynomial makes you look like a Boolean poset, then you must be Boolean. I feel like that's true, but I have to think about it a little bit. Yeah, maybe not. I'm not sure. Okay. Why does a characteristic polynomial factor? This one factors. It doesn't look like it should factor, right? What we did there is not multiplicative in any way. Right? It's just adding some numbers that we computed in some mysterious way, and then you kind of add them all, and it gives you this thing that factors. It is an interesting phenomenon that very often characteristic polynomials factor for interesting reasons. Here, there's an easier reason. When you have an equation and one side factors, you should think, okay, does the other side factor? So can you say that bk factors in some sense? And in what sense? Yes? How do we factor bk? How do we factor a poset? We split it up into factors where multiplication is a product. How do we express bk as a product? Remember? The Boolean poset bk is exactly b1 to the kth power. And it's just, like, this is a three-dimensional cube. It's a segment, cross a segment, cross a segment. Okay? And in general, bk is just b1 to the k. Okay? And so could it be true that this is q minus 1 to the k just because bk is b1 to the k? It turns out that that is true. Okay? And so here's another nice lemma that is useful. If p and q are graded, then p times q is graded, and the characteristic polynomial of p times q is just the product of the characteristic polynomials. And I should say that even if p and q are not graded, so if p and q are not graded, then you cannot talk about the characteristic polynomial because you don't have ranks. But still, the Mobius function is also multiplicative. So if you want the Mobius function of p times q, it is, in a very precise way, the Mobius function of p times the Mobius function of q. And I wrote it down in the notes. So I'll let you look at that formula in the notes. And I didn't write this one in the notes, so let me write this one here. Okay, that's a nice lemma. Very useful. And again, it's a lemma that if you want, you can prove it by hand. But we now have a solid enough framework that you can probably imagine there's a conceptual reason for this. And the reason is that P times Q is just a multiplication in the Hopf algebra. Okay? And the characteristic polynomial comes from the antipode. Okay? And so if I tell it to you in that way, it's not so surprising anymore, because we know that the antipode is multiplicative almost. Right? The antipode is multiplicative, but it switches your variables. But if you just, I mean, if you know that, then maybe this is not so surprising anymore. And if you just write out what you need to prove, you'll see that this follows precisely from the fact that S of the antipode of P times Q is the antipode of Q times the antipode of P. Okay? You might be concerned with the fact that P and Q are switched. This is not a commutative equation. But when you move to Mobius functions and characteristic polynomials, then we're in polynomial land, and so these two are commutative, and that's why it doesn't really matter. Okay? So, I mean, this is more like a proof sketch, but it really just comes down to this. Okay? I think I'm running out of battery, so I don't know. What did you think of what? Somebody tell a joke while I do this, because it's going to take me a minute to find the next battery. Huh?
I think you can make a variant of B3 not B3 that has the same. You take just one of the segments joining the.
Mm-hmm. So that's great. We have a joke and a theorem. All in the course of changing microphones. So okay. What do you want first, the joke or the theorem? First, the theorem. So Seth is telling me that he has an answer to Servando's question. He's going to give me a different poset with the same characteristic polynomial. And what he says is that he's just going to take one of these and then move it anywhere else, maybe? Except that you could also move it like from here to here. I mean, there's a couple of things you could do, but
I see what you're saying, yeah.
But that.
From the same place, but to somewhere.
There you have it. Yeah. So the Mobius function is exactly the same, right?
What is the join of?
Oh, it's not a lattice anymore. Right? So, yeah, this is not a lattice. They don't have a join, but it doesn't matter. Because this can be done for any poset. So here we have an example of two posets with the same characteristic polynomial. So that answers that question. This is not B3. This is like B3 to B3 something. B3 changed. Okay? And then the joke. What's the joke? I got to give you the microphone. No, you got to do it. You got to do it.
What did 0 say to 8?
What?
Nice spell.
I like it. I knew it already, but it's a good joke. Actually, that's a very good joke for this class. You can think of a more advanced answer to that question. What does 0 say to 8? It's going to be your homework question. Make up a Hopf algebra joke that starts with what did 0 say to 8? That's your homework. We'll take it to the forum. You get it? You get it? Think about it. It's not a good joke, but it is good with the kids. No, your joke is good. The one that I have in mind is not good. Okay. All right, thank you for helping me make that battery transition so smooth. You guys are good. Okay, so we computed this, we computed the Mobius function of the Boolean Postit. Let's do another example. The chain Ln, okay, where you have n links. Okay. So again, you might remember that we already computed this antipode. Actually, you did this in your homework, right? And so given that you have the antipode, you have the Mobius function. What does the antipode look like? Do you remember? Some sum, right? So I'm going to write this down. The sum. So you might, I guess there's different ways of writing this, but basically, this is one of the ways of writing it. It is the sum over all different ways of writing n as a repeated sum of a bunch of p1s, a bunch of p2s, etc., a bunch of pk's. And then you get something times L of LP1 to the alpha 1 up to LPK to the alpha k with some coefficient. And the coefficient look like this. Okay. You did this, it's in your homework. And so, and this is the best possible formula for this antipode, which is maybe a little bit of a letdown because it was a pretty simple poset, right? But the antipode is not so nice. So that means that we have a formula for the Mobius number of Ln, right? Because all we have to do is apply zeta to both sides. So if I apply zeta to both sides,
Was that really the p greater than 1 or greater than 0? Because I thought that would force you to have. Oh, but k can be whatever. Okay.
I think this is right, yeah. So now I'm going to apply zeta to both sides. So if I apply it on the left, well, I'm just going to leave it like this and say that this is equal to mu of Ln. Okay. What happens when I apply zeta to the right-hand side? But remember, all that zeta does is that whenever it sees a poset, it turns it into a number 1. And so all it does is that it gets rid of this. That's not there anymore. It just turns all of those into a 1. And so there's your formula for the Mobius number. The Mobius number of Ln is this sum. Okay. Do you like it? It's a little bit less exciting than the previous one, right? And let me, I mean, it's, you know, it's hard to even compute this sum in an example. Like if I ask you what mu of L4 is, then you would have to look at all the ways of writing 4 as a sum like this, and then compute all these things, blah, blah, blah. So it's a formula, but maybe you're not really thrilled to use it.
Right. I just want to remind her why we're supposed to be excited about the Mobius function again. Is it because we can get to the characteristic polynomial?
I'm going to tell you more about, I'm in the process of trying to get you excited about the Mobius function. So far, I've just given you an example that shows that in some examples it's nice. Okay? But I'm going to give you some applications of the Mobius function in a minute. Now, the point that I'm trying to make here is that, okay, the antipode gives you a formula, but what is really the Mobius number of this poset? You can actually compute it by hand. It's not very hard. Start at the bottom and work your way up, right? So let's do it. Okay, that's Ln. Let's compute the Mobius number of Ln. So you start at the bottom and you get a 1. Then here you add the things below it and you change the sign. Then here you add the things below it and you change the sign.
0, 0, 0, 0.
So you see this formula sucks. This formula is no good. Really, the formula should just be 0, right? That's unless n is equal to something very small. Right? So really, the real formula, the good formula, is this. It's 0 usually, minus 1 if n is equal to 1, 1 if n is equal to 0. Okay? So maybe you can think of this as one of two things. First of all, you should be warned that sometimes the antipode is not going to give you your favorite formula for the Mobius function. This is obviously better than this. But then, okay, if you're an optimist, then you can see the good side of anything. And the good side here is that now you have a theorem. This is equal to this, which is not obvious at all. Right? Maybe you wouldn't call it a theorem, but it would be a nice combinatorics exercise that I might say for the next time I teach combinatorics. Prove that this sum is equal to 0, unless n is very small. So, okay. But that's that. Okay. The problem with me teaching this is that I like Mobius functions a lot, and I could spend a very long time talking about this. But I need to make, there's a couple of points that I really want to make today, so let me. Okay, another example, and then we'll get to why this is very useful. But a very important example is the poset dn, which is the poset of divisors of n, ordered by divisibility. Okay. So we've done examples of this. Let's say if n is equal to 120, I can do this. For any n, I can do this. It's not very hard. And the reason is that all you have to do is factor this number. So that's the hardest part. So 2 to the what? This is 8 times 15. So 2 to the 3 times 3 times 5. Okay. And then this is just going to look like you just give a direction to each one of these. I mean, the point is that this poset is just the poset L3 cross L1 cross L1, where these are the exponents. And we've done this a couple of times. We've done it in this class. We actually did it last semester. If you took algebra from me. So you just kind of give a direction to the primes in each, give a direction to each prime. Okay. So 2 to the 3, 3 to the 1, and 5. Okay. And then you just kind of take joins, and you get a box. It's going to look like this. Like that. Okay. And for example, the number here is 4 times 5. Is it? 3 times 5. So let's compute the Mobius function of this poset. Okay. So I want to compute mu of a comma b for any a and b where a divides b. Okay. So let's do it. For example, what is mu of 2 comma 60? you've noticed that mu only depends on the poset. It doesn't depend on the stuff, on the interval that you're computing, not on the stuff outside. What is the interval between 2 and 60? That's just the poset of divisors of 30. Right? These are the divisors of 60 that are multiples of 2. So this is the same thing as this thing. Is the same thing as the poset of divisors of this divided by this. In this case, it's 1 and 30, but in general, if this is a and b, then these are the divisors of b over a. Okay? And so let me say that the interval from a to b is isomorphic to the poset of divisors of b over a. And that means that if you want to compute mu of ab, you just need to know how to compute mu of the divisors of something, where k is equal to b over a. Okay, so how do you compute mu of dn? Well, mu of dn is equal to what? The key is that dn factors, and therefore mu factors. Okay? So how does it factor? That depends on the prime factorization of n. So if n is equal to p1 to the alpha 1 up to pk to the alpha k, that means that dn is mu of L1 to the alpha 1. Dn is equal to L alpha 1 times, etc., times L alpha k. So mu of dn is going to equal the product of these mu's. Okay? Because we just said that mu is multiplicative by this lemma. Okay? I mean, here I said that the characteristic polynomial is multiplicative, and I told you that mu is also multiplicative by the same reasons. Okay? So what is this number? Well, one thing you should notice is that in the prime factorization of a number, all the exponents are at least 1, right? Because if alpha k is 0, then you wouldn't put that prime there. Okay, so all the alphas are 1 or bigger, and so these are mu of L sub something where that's 1 or bigger. Okay? And we know what mu of L sub something is. It's either, if n is 1 or bigger, then it's either minus 1 or 0. It's minus 1 if alpha is 1 and 0 otherwise. Okay? And so what we're going to get is that this is going to equal 0, usually actually. Right? As soon as one of these alphas is 2 or bigger, it's done. If some alpha I is greater than or equal to 2, and minus 1 to the number of factors otherwise. So minus 1 to the k if n is just p1 up to pk. Okay? Let me say this a little bit differently because we want the answer in terms of n only. What does it mean that some alpha I is greater than or equal to 2? It means that some prime appears twice in the prime factorization. So let me just write this by saying if p squared divides n for some prime p. Okay? So the Mobius number of the positive divisors of dn is 0 if n is divisible by some square of a prime. And if it's not, then it has to be a product of primes. And the number is just minus 1 to the number of primes. Does this look familiar to anybody? So if you've learned about the Mobius function for number theory, there it's even more mysterious than what we're doing here, because they just say, oh, you know, define the Mobius function to be this. And then you think, what are they doing? Why should I bother to define this, and why is it interesting? And hopefully now you see that this is part of a much bigger context, and that you were only seeing a very small part of the story, which is why the story didn't make any sense. Okay? But this is how you land at the right definition of mu. Okay? Now, the point of that is that, and I think historically, actually, this is the first application of what's called the Mobius inversion formula. So if you've seen this in number theory, then you know this is a very useful formula, a very useful function in number theory. I'll remind you how. And the point is that what you did there in number theory applies to any poset that you can think of. And that's, I think this was Roda's realization, that number theorists were doing this a long time for divisors in a very limited context, but he realized that it extends to any poset given what we're doing here. Okay? So, okay. So let's talk about actually applying this formula. There's something called the Mobius inversion formula. You proved it in your homework, and you probably had no idea why you proved it in your homework. And now we'll see. Now we'll see why. So Mobius inversion formula. Let P be a poset, and let f and g be functions from P to somewhere, some field. Here, I'm using a different, I've been using K for the field, because K is kind of a ground field that we keep working with. But here, I'm changing the letters so you can think of this as just any field you want. It can be numbers, but it can also be the field of rational functions. It can be the field of rational functions in any number of variables. Basically, these are just some ways of assigning to a poset something. A number, a polynomial, a rational function, it doesn't matter. Okay? If g of each element of the poset is equal to the sum over there's two versions of this, and I want to write the one that I'm going to find more useful. If g of x is equal to the sum over y greater than or equal to x of f of y, then for all x in P, then f of x is going to be the sum over all y greater than or equal to x of mu of xy g of y for all x. Okay? That's the Mobius inversion formula. It's an inversion formula because it basically, I mean, the way this usually goes is that you have a function f in mind, and then g is defined in terms of f in this very specific way. Okay? Think about it this way. So these are functions from a poset to somewhere. So you're just thinking you have your poset, and to each element of the poset you assign a number or a polynomial. It doesn't matter. Okay? So f is some assignment like that, and then g is obtained by g of x is the sum of all the f's above x. Okay? So g is very explicitly defined in terms of f, and now the question is, can you now reverse that relation and write f in terms of g? That's why it's called an inversion formula. And you can, and you get exactly the same formula, except that the Mobius function comes up. And so this is a very natural reason to study Mobius functions, because we have this kind of thing very often in combinatorics and in number theory and in several places. And whenever you want to invert something like this, the Mobius function just comes up. So let's do some examples of this. Examples of this Mobius inversion formula. And I wrote in my notes in parentheses that this is just a few of many, many examples that exist out there. Okay? One example is something called the inclusion-exclusion formula in combinatorics. And it says the following. You have S, and S is usually some kind of set of properties that an object can have. Very general. I'm being very vague because this is very general. If you're taking the GRE, then the properties are plays soccer, is blonde, and is tall, and these are properties that people can have. Okay? And then you say for every subset of S, you're going to say that f of t, we're going to say that g of t is the number of people or number of objects or whatever, number of objects having the properties in T. So that might be the number of people that are blonde and like soccer. And f of t is going to be the number of objects having properties T and no others. So that might be the number of people that, what did I say? Blonde, like soccer, and are not tall. They don't have the other properties. Okay, so this is more restricted than this. Okay. So one thing you'll realize is that what? Is that if you are an object and you have properties T, that means you have properties T and maybe possibly other ones. So this is going to be, let me switch letters here. So if you have properties A, that means you have properties A and possibly other ones. So we're going to sum over all the sets of properties containing A, and we're going to sum the people that have exactly the properties in B. So what I'm saying here is that if you're blonde and you like soccer, then either you're blonde, you like soccer, and you're tall, or you're blonde, you like soccer, and you're not tall. Okay. So those are the two terms here. Okay. Therefore, we can apply Mobius inversion. Yes. So maybe I'll say that in a second. But for now, let me just say f of A is just the sum. I mean, Mobius inversion says, sorry, B is. I mean, you'll see that this is precisely Mobius inversion in the poset of subsets of S. Right? This is a subset of S, and these are the subsets bigger than it in the Boolean poset. And so I apply Mobius inversion, and I get this. Okay, and this is something that can be simplified because we already computed the Mobius numbers of the Boolean poset. We know that this is just -1 to the something, right? It's -1 to the B minus A G of B. And this is what's called the inclusion-exclusion formula. And really, I mean, I don't know how much the GRE has changed since I took it, but when I took it, this question had to be there. They gave you properties, and then they told you, you know, this number of people. And even the SAT, they had questions like this. They tell you this number of people like soccer, this number of people like soccer and volleyball, this number of people like basketball and soccer, and then you had to answer how many people like volleyball and basketball but not soccer. And this is precisely how you do that. Okay, but this is kind of a lot of work to do to answer a GRE question. But the point is that actually this is a very ubiquitous theorem in combinatorics. Ubiquitous means that it's all over the place. I learned that word recently and I like it. So this is all over the place, and so I'm going to show you one example of inclusion-exclusion. So the first example of Mobius inversion was inclusion-exclusion, but now let me give you an example of inclusion-exclusion so that you see the kind of things that combinatorials do with this. And this is it's a pretty famous problem that probably if you take a course in probability, you're going to learn it at some point. And it goes like this. It says that there's a party. There's only men at the party. There's n men at the party. They're all fancy and they're wearing these nice hats. And they all have very good manners, and you're not supposed to wear a hat indoors. So when they come in, they leave their hat at the door. And then they go and they forget that they're polite, they get really drunk, and then on the way out, they just kind of grab a random hat and leave. And then the question is, what is the probability that no one got the right hat? And there's probably some name for this problem. But let's say it in the language of combinatorics, you basically have you're just picking a random permutation, right? You have people, you have hats. And if your hats are numbered 1 up to n, then when the drunk people leave the party, they're just, in any order, rearrange the hats. And so the question is, how many permutations of the numbers from 1 up to n don't leave any element fixed so that nobody has the right hat? These are called derangements. Funny name, derangements. They're also called dn usually, but so let me put lowercase n. dn is equal to the number of permutations pi, the numbers from 1 up to n, such that no element gets the right hat. Pi of I is never equal to I. So the probability in the drunken man situation is basically the arrangements over n factorial. Okay. So let's compute this. The kind of problem where this works is when you're trying to count something that works for all I, and then this lets you turn questions about all I into questions about some I. That's kind of the intuition. Okay. So let's say, let's define a bunch of properties. S1 up to Sn. The property Si is the property that pi of I is equal to I. Okay? That's a property that a permutation might or might not have. Okay. So now let's compute G of T. Okay. Number of permutations having the properties in T. Okay, so maybe T is equal to SA some set of the properties. Okay. So what am I counting here? I'm counting the permutations such that pi of I is equal to I for these values. Pi of A is equal to A, pi of B is equal to B, etc. Pi of C is equal to C. Okay. How many permutations are there? Well, here are the numbers from 1 up to n. I need to rearrange them. I know that there are some special elements of my permutation that I am demanding have to stay fixed. And I can rearrange the other ones however I want. How many ways do I have of doing that? It's basically just the permutations of the other stuff. So this is just n minus k factorial, where k is the number of elements of t. Okay? So g of t is very easy to count. What is f of t? F of t is the number of objects having properties t and no others. So you can now answer the question, how many permutations fix 3, fix 5, fix 7, and don't fix anybody else? Right? Which is the question that we have. What we want actually is the permutations that don't fix anybody. So what is that called? Dn is the number of permutations having none of the properties. Right? Having none of the properties. So what is that in this language? It's f of the empty set. Right? Having the properties empty set and no others. You have none of the properties. Okay? So this is just f of the empty set. Okay? And the inclusion-exclusion formula tells us what that is equal to. This is equal to the sum over all the b's contained in the empty set of minus 1 to the b minus empty set g of b. Okay? Now, it's pretty easy to contain the empty set. So we are summing over all the possible b. When you subtract the empty set, you're not subtracting anything. And g of b is n minus the size of b factorial. Where we're summing over all the subsets of n. Okay? Now, what we can do is we can say, okay, now let's sum these by cardinality. So how many b's have size k? We're looking at all the subsets. Let me say that if b has size k, then it contributes minus 1 to the k times n minus k factorial. And how many sets b have size k? We're looking at subsets of n that have size k. So this is n choose k. Okay? Now this is actually something that simplifies because this is minus 1 to the k n factorial over k factorial n minus k factorial times n minus k factorial. So we get this. And I can actually pull out the n factorial. And I get the sum minus 1 to the k over k factorial. Okay? And so the probability of no correct hat is this divided by n factorial. which is the sum over k equals 1 to n. Sorry, k, this goes first k from 0 to n, right? So k from 0 to n of minus 1 to the k over k factorial. But I hope this looks familiar to you from your analysis class. If this was an x, then this would be the power series for e to the x. Right? And actually, it converges very, very quickly to that because you have these factorials in the bottom. And so this is basically e to the x, where x is negative 1. And so this is 1 over e. Okay? And it converges very, very quickly to 1 over e because of the factorials. And you can quantify this with the right analysis. So I mean, I think this is a really beautiful way of, first of all, if people don't believe the importance of E, well, okay, here's a very like pedestrian way of running into E. Okay? But yeah, so this is one of the kind of prototypical applications of inclusion-exclusion, and hopefully this begins to show you. I mean, this is just the first example of what Mobius inversion is about. And so the point is that now you can do this, but instead of doing it for subsets, you can do it for any poset that you can think of, which is great. Okay. Like I said, I could talk about this for a whole semester, and I might at some point, but I'm not sure if I'm going to say what. I had a number theory example that I was going to do, but I promised you next time I was going to switch topics. So I'll decide between now and next time if I'm going to do the number theory example. But you might just look at the notes and look at it to see what this looks like for Mobius inversion in number theory. Okay?
Are you computing the complement to the event?
Are
you computing?
Probability, no, correct hat is the probability that
There is at least one correct hat when you were doing geometry.
I'm computing f of the empty set, which is that you have none of the properties. And that means that nobody has the right hat.